All right, today we're going to talk about permutations and counting. And so we're going to explain the difference between permutations and combinations, and we're going to use the counting principle, and we'll talk about what factorial notation looks like. So first of all, there's two different formulas that we will be using. One is for a permutation, and that's when order matters. And we'll talk a little bit more about that on the next few slides. When we're talking about permutations, we usually are using that capital P. And this is the formula that we're going to use, which is kind of scary looking when you look at it for the first time. We'll get into more what that means in a second, but combinations when order doesn't matter. So when you think about it, when you type in your password into a computer, it's a permutation because the order is going to matter, okay? But when you call up Domino's and order a pizza and you ask for a pepperoni and sausage pizza, it doesn't matter if you say a pepperoni and sausage pizza or a sausage and pepperoni pizza. You're going to get the same pizza anyways, and therefore order doesn't matter. So there's a little bit of a difference. Now, when you're looking at these two formulas, they actually look really similar. A little bit scary for both of them, but pretty similar. The only difference is this formula has an extra r factorial in the denominator. So that's going to change things for that a little bit. Okay. So going back here then, we can see that these formulas are pretty similar, and we need to know what the n and the r stand for. So the n is the total number, and the r is the selected amount. Okay, and that's true for the n and the r over here as well, so that's going to stay standard. Okay, now a permutation can be used whenever we're arranging a certain number of objects in order without repetitions. That without repetitions part is pretty important. And a combination can be used whenever we are choosing a group of items from a larger pool of possible items. Another example is, I think student government elections are coming up soon, and so you have a pool of people that will be applying for, student government president, and they'll select, and vice president, and all those things, and so they'll select from that pool, and order actually doesn't matter. So that's just another example. Okay, that formula. This might be the cause of that. If you are dividing by more of something, wouldn't it make sense that sometimes... Now, this will help us actually see a little bit more of what the difference is between permutations and combinations. If I have the letters A, B, and C, when I'm counting permutations, every time I switch the order of the letters, it counts as a new permutation. There, I think I got all of them included there. So there's 6 total possible permutations. How many combinations? Well, A, B, and C, it's all the same letters. It doesn't matter how they're arranged, so there's only one combination. Now, I just want you to think about this for a minute. Notice how there's more permutations than there are combinations. If I just go back, you get a smaller number. So just think about that, okay? All right, so we also have to talk about counting principle. And this is what the definition like you'd find if you had a textbook. It says, suppose there are n ways to make a choice, and for each of those ways, there's n more ways to make a second choice, and so on and so forth. Now, the way you know this is by making a tree diagram. If Judy has 4 different shirts, you would draw 4 different branches off of that, and then 3 branches for each pair of pants she chooses off of each one of these, right? Well, we want to try and get away from drawing all those tree diagrams to find out how many different outcomes there are. So instead of drawing the tree diagram, we can narrow it down by using the counting principle to just be saying there's 4 different shirts and 3 different pairs of pants. We do 4 times 3, so there's 12 different outcomes that she could have for her outfits. Now, they add another part to this. So if we were to draw a tree, she still has her 4 shirts and 3 different pairs of pants coming off of each one of those. And then 2 pairs of shoes. Oh my goodness. My tree diagram's not organized enough. But you get the point, right? we don't really want to have to draw this out. And then 2 necklaces and 1 pair of earrings. So if I were to use the counting principle, I would just say 4 times 3 times 2 times 2 times 1. Okay, so what is that? 12, 24, 48. 48 different outcomes that we could have. Now, in this first problem, it says how many different license plates are possible, assuming 3 letters followed by 3 numbers. Well, right away we know when we're talking about license plates that order matters. So we're dealing with a permutation. Now, in the definition of permutation that we started with, it said that the letters or the items cannot repeat. But we know in a license plate that they can repeat. So we have to use a different setup for this problem. So when we think about it, there's 3 letters of the license plate. So all of these are letters. And there's 3 numbers. When we're setting this up, we know that there's a total of 26 letters, okay? And then there's 26 letters that could be used again and 26 letters that could be used again because they repeat. Well, we know that's true, and we can use the counting principle to multiply those things to be able to find out how many different outcomes there are. Now, a mistake that a lot of kids make when we're dealing with numbers, they think of 1 through 9. But a lot of times they forget 0. 0 is a digit that could be used on a license plate as well. So there's actually 10 digits that could be used. And those digits can also be repeated. So right now on my calculator, I'm taking 26 to the third times 10 to the third. And I get 17,576,000 different license plates that could exist. And that's a lot. And I've also noticed in Minnesota they have numbers first and then letters, which just basically doubles the amount that we just talked about. So the next problem is a little bit more complex. It says, what is a probability that a license plate has no repeated letters or numbers? So the order still matters. It's still a permutation. We start with letters and then followed by numbers. Except now we start with 26 letters, but if I use L in the first letter, I can't use L again, so I'm down to 25 letters after that, and then 24. It says no repeat letters or numbers, so in this case I have 10 digits I'm working with, but then after I put a digit in that first spot, like let's say it's 6, now I'm down to only 9 digits to work with or choose from, and then 8 digits. So I'm going to put this into my calculator. So we get 11,232,000 different ways. That significantly cuts down the number of license plates by a lot, like 6 million. So in this problem it says 3 boys, Greg, Sam, and Tyler, and 2 girls, Patty and Sarah, compete in a race. There's first, second, and third place prizes are awarded. Find the following. How many different ways can the 5 racers place? Well, we're just looking for all the racers placing. The only thing that I'm thinking about, it could be taken 2 different ways. Are we just looking for first, second, third place, and those are the only ones that place? I'm not sure. We're going to go with how all 5 of them place, okay? It's a little misleading there. So when we look at the first place position, there are 5 different kids, 3 boys and 2 girls, that could be selected for that spot. Once one of them finishes first, now there's only 4 kids that could be selected for second place, 3 for third place, 2 for fourth place, and 1 for fifth place. Then it says, how many different ways can the 5 racers place if a girl needs to finish first and third? So let's just narrow this down to just first, second, and third place. We had 2 girls to choose from, Patty and Sarah, and they both need to finish first and third. So when I think about first, there's 2 girls that could finish. It could be Patty or Sarah. But then when I go to third place, I only have 1 female left to choose from, and it's either going to be Patty or Sarah, whoever is left over and didn't get chosen for first. Who am I going to pick for second place, though? Well, that's going to have to come from the boys because I used up all the girls already, and so there's 3 kids left over. And so there's 6 different outcomes where that could happen. Then it says, what is the probability that a boy finishes second? Now, okay, I kind of already know this. I have to find the total number of ways that kids could place first, second, and third. So maybe this first one was asking, this number 1 was just asking for first, second, and third. So I'm going to say 5 times 4 times 3. So 20 times 3 will be 60. So there's 60 different total outcomes. That's our total number of possibilities. That's going to go in the denominator because it's asking probability. And the probability that a boy finishes second. Well, in this case, we have to think about for the numerator, all we care about is that a boy finishes here. We don't care who's in first and we don't care who's in third. So there's 3 boys to choose from there for that second place spot. But once I select a boy, we're down to only 2 boys. For first place, it could be those 2 boys that were left over, or it could be one of the 2 girls. So I have a total of 4 choices for that first slot. One of those kids will be selected. It doesn't even matter if it's boy or girl. And so there will be 3 kids left for this slot. So it got a little sloppy here, but this is going to go up here and this is going to go down there. So 4 times 3 is 12, so I get 36, and my last step is just to divide those 2 things. I get 0.6. All right, so it says you and 7 other swimmers. So 8 people total compete in a race. How many different possibilities can the swimmers place first, second, and third? Again, this whole first, second, third place business is all permutations. So there's 8 kids that could be selected for first. Once one is selected for first, they can't be first and second. And so we just end up with 8 times 7 times 6, so 336 different ways they could be selected. How many ways can the swimmers place if you finish in second place? So there's only 1 kid, you, that finishes second. Now we have 7 kids left over that could have been in first. And then after we select somebody for first, there's only 6 left for third place. So we get 42 total different ways. This one gets to be a little bit tricky, so we're going to skip the last one. How many different 5-digit zip codes are possible? Again, order matters. We're thinking zip codes, obviously digits can repeat because a lot of the zip codes around here start with 55. We have 10 total digits, and they can repeat. So it's like taking 10 to the 5th, which is 100,000. What is the probability that the first 2 digits of the zip code are 55? So we have 1 choice here, 1 choice here. This is going to help us count up the total number of ways that you could just have your zip code starting with 55. Then after that, there's 10 digits that you could choose from. So that ends up being 1,000, but we have to be careful because I notice here that it asks for probability. So I have to divide that by the total number of ways there are. So I'm going to divide by 100,000, what I got from part A, and that's the probability then. So how many zip codes are there if you could only use each digit once? So if I use each digit once, I have 10 digits here, 9 digits, 8 digits, 7 digits, and 6 digits. So I get 30,240. And what is the probability that the last digit of a zip code is 7 if there are no repeat digits? Okay, so we got to think about this one a little bit harder. It's kind of like a given. Given there's no repeats, what is the probability that the last digit is 7? So first of all, how many ways could that happen? This has to be a 7, so there's only one option there. After that, I'm going to go back to this first spot, but I already used 1 digit. I used a 7, so now I'm down to 9, 8, 7, and 6. Now be careful. This one also asks for probability. So I'm going to divide it by something. divided by the total number is kind of like it was given that there's no repeat digits. So I'm going to bring this part down here. So 9 times. So I get 3,024 divided by 30,240. I get 0.1. Okay. So that should help you out. There's a permutations and accounting worksheet for you. Yeah, good luck to you guys. Let me know if you have any questions.